Think about how a child learns to ride a bicycle. No one hands them a labeled dataset of 10,000 images of successful bike riding. No one gives them a rule book. They just try. They fall. They notice what went wrong. They adjust. Eventually something clicks, and they're riding. That simple loop, act, observe, adjust, is the oldest form of learning we know. It's how animals learn, how humans learn most physical skills, and how increasingly we teach machines to solve problems that don't fit the supervised learning paradigm. This is reinforcement learning. In this lecture, we'll build the mental model you need to understand why it works, where it works, and what makes it different from everything else in machine learning. Every reinforcement learning problem reduces to an interaction between two things, an agent and an environment. The agent is the decision maker. This could be a robot, a game-playing AI, a trading algorithm, a chess engine. The environment is everything else, the world the agent acts in. At each time step, three things happen. First, the agent observes the current state of the environment, call it S sub T. Second, based on that state, it chooses an action, a sub T. Third, the environment responds. It transitions to a new state, S sub T plus 1, and hands the agent a scalar number called a reward, R sub T plus 1. Higher is better. And then the whole thing repeats. State in, action out, new state, and reward back, forever, or until the episode ends. That's it. That's the entire framework. Every RL problem you'll ever encounter, AlphaGo, the RLHF training behind ChatGPT, robot locomotion, recommendation systems, autonomous driving, fits inside this loop. Let's make this concrete with the simplest possible example. A grid world. Imagine a 4x4 grid. An agent starts in the top left corner. There's a goal in the bottom right. Reaching it gives a reward of +1. There's a pit somewhere in the middle. Stepping into it gives a reward of -1. Every other step gives a tiny negative reward, say -0.04, to encourage the agent to finish quickly. The agent has 4 actions: up, down, left, right. It doesn't know the layout in advance. It doesn't know where the goal is. It just acts, receives rewards, and remembers. In the first episode, the agent wanders randomly. It might fall in the pit. It might hit walls. It might take dozens of steps to stumble into the goal. But every step, it's logging. I was here. I did this. I got this reward. I ended up there. After enough episodes, something remarkable emerges. Without being told what the goal is, the agent learns a policy, a mapping from states to actions, that navigates to the goal efficiently. It has, in a meaningful sense, figured out the environment. This is where RL gets philosophically interesting. Notice what the agent was optimizing. It wasn't trying to find the goal. It was trying to maximize cumulative reward. The goal was reachable only as a consequence of that optimization. This idea is important enough that it has a name. Richard Sutton, one of the founders of modern RL, calls it the reward hypothesis. That all of what we mean by goals and purposes can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal. That's a big claim. It says intelligence, at least the goal-directed kind, can be reduced to scalar reward maximization, given a rich enough environment and a capable enough agent. You can debate whether that's fully true. Many researchers do. But the practical consequence is this. If you can specify what you want as a reward function, you can, in principle, use RL to optimize for it. This is why RL has become the backbone of so much frontier AI. It's how we turn "here's an objective" into "here's a system that pursues it." In the next lecture, we'll move from this conceptual framing into the math, how the agent actually turns those rewards into a policy. We'll meet the Bellman equation and Q-learning. But everything we build from here rests on the loop we just drew.